Alright, silly people, here's the situation. We have a wave function that we're going to have be subject to a potential v equal to v naught minus I gamma. Um, and we're trying to prove that the probability that you find said wave function anywhere is going to be, the time derivative of that is going to be minus 2 gamma h bar times p, which is kind of funny. So, I mean, let's first of all just look at the probability. Then the probability that we find it anywhere is just the integral from minus infinity to infinity of the square modulus of the wave function integrated over space. Um, so if we take a time derivative of that, uh, it's going to look like d dt of minus infinity to infinity psi squared dx, and then you can move that time derivative in to the integral by turning it into a partial derivative. And now this is the partial derivative of, I'm going to expand the definition of the square modulus as being psi star psi, right? Um, so then you can expand that using the product rule. So that'll be psi star del psi del t plus psi del psi star del t, and that is going to be integrated over space. So at this point, it's worth looking at the Schrodinger equation, the time-dependent one. So that's going to be h bar del psi del t is equal to minus h bar squared over 2m del squared del x squared of psi plus v, the potential acting on psi. And in this particular situation, we have a potential that is a constant complex number, where it's going to be v naught minus I gamma acting on psi. We can actually solve this for del psi del t as being h bar I over 2m del squared psi del x squared plus, and this is going to be actually minus v naught I over h bar, and it's going to be minus gamma over h bar. These are both acting on psi. You can actually also take the complex conjugate of this equation, and it will be necessary for this problem, so might as well just taking the complex conjugate of everything involved plus v naught I over h bar psi plus, alright, this is still minus gamma over h bar psi. That is looking good. So we can plug these definitions into our integral now. So dp dt is now looking like the integral from minus infinity to infinity. You got, I'm going to open the brackets, you got psi star, then you have del psi del t, which is h bar I over 2m del squared psi del x squared minus v naught I over h bar psi minus gamma over h bar psi. We just found that. And then you also have psi times del psi star del t, which is minus h bar I over 2m del squared psi star del x squared plus v naught I over h bar psi star minus gamma over h bar psi star. I guess I forgot to write the stars on that last line. Star here and star here. Good. That's what we're integrating. And I'm going to group it together in a way that is a little bit more suggestive to what we're doing. Um, First, let's get the stuff that depends on h bar I over 2m, which is going to be the integral of, we'll have psi star del squared psi del x squared minus del squared psi star del x squared psi integrated over dx. And then we'll group together the stuff that is dependent on v naught I over h bar, which is just looking like psi star minus psi star psi, which is 0. Those cancel out. So we're not even going to look at those. And then you have a couple of minus gamma over h bar psi star psi's. So I'm going to write this as minus 2 gamma over h bar from minus infinity to infinity of psi star psi. Now for this thing, the way to approach it is to do a couple different integration by parts. So I'm going to have u1 equals psi star, so that du1 is equal to del psi star del x dx, and then we'll have dv equals del squared psi del x. Oh my god. Del x squared dx, and then v, that's v1, is del psi del x. For the second part, we'll have u2 equals psi, du2 equals del psi del x dx, dv2 is going to be del squared psi del x squared dx, and then that integral of that is going to be del psi del x dx, right? And so in all, we have that our integral is going to look like dp dt is equal to h bar I over 2m, and then we have this stuff in here which is carrying out integration by parts. So u1 v1 is psi star del psi del x, evaluated from minus infinity to infinity, which is 0, because whenever you evaluate wave functions at infinity, they should go to 0. And then you have minus the integral of v du, so minus to minus infinity to positive infinity of del psi del x del psi star del x dx. And then we're going to evaluate the other integration by parts, so minus u2 v2, so it's psi times del psi del x. One of those is supposed to have a star on it, yeah. I guess it's the complex conjugate. Yeah. So it's complex conjugate there. And then you evaluate those at the endpoints, minus infinity to infinity, which also goes to 0 by the same token. Minus the integral v du, which is going to have a plus sign on it this time. So this is going to be del psi star del x del psi del x dx. And then now it's not too hard to see that this term is the same as this term with different signs, and so they cancel out. Uh, so that was cool. And so all that we have left over is this 2 gamma over h bar psi star psi, which you can change that into the square modulus of the wave function, because that's the definition of the square modulus. So you find that dp dt is equal to minus 2 gamma over h bar. And then you can use the definition that Griffiths gave you for probability to say that it's just the probability, that integral. So yeah, I found that dp dt is equal to minus 2 gamma over h bar p. Fantastic. Now, the next part of the problem is interesting. He tells you that the probability is going to look like e to the minus t over tau, right? So using that on both sides of our equation, we have that d dt e to the minus t over tau is equal to minus 2 gamma h bar e to the minus t over tau. Taking the derivative of this guy, you have that it's just minus 1 over tau e to the minus t over tau. And then this is minus 2 gamma over h bar e to the minus t over tau. And so now it's just a little bit of algebra. Cancel this thing out with this guy. The minus signs cancel out. And then you can flip the fractions. So you have tau equals h bar over 2 gamma. So I guess that's how long a particle lasts in a potential like this. All right.